Hello and welcome to the Maths to Diagnostic question of the week number 21 with me, Craig Barton, where each week I pick out a question that has been answered from my Diagnostic Questions website and we take a look at the figures. How many students have gone for each of the four possible options, but far more importantly than that, we look in depth at the explanations students are given for those choices that they're making, because it's those explanations that give us a real deep and useful and meaningful insight into the way students all around the world think about certain topics and concepts and the mistakes and misconceptions that they may have. Now, I'm dead happy at the moment because the number of answers on the website has just crossed the 250,000 mark and we've got 44,000 students on there now. And the more students and the more answers we get, the more we learn about the way students all around the world understand mathematics. So keep spreading the word of the website. It's all completely free and then we can all benefit from that. Now, we haven't done a shape and space question for a while, so I fancy doing one of those this week. So, as ever, data questions page is the best way to start. This is automatically filtered by most incorrectly answered questions. Often I like to go for most answered because that gives me much more data to play with. And as I scroll down here, you'll see some questions that are very familiar to people who've been following the Question of the Week series. I fancy going to page 3, because I think this is where the question I want is lurking. And there it is there. A lovely little area of a triangle question. So let's fire that one up. So at this point of the video, you might want to pause it and ask yourself 3 questions. Firstly, what is the correct answer to that question? Secondly, what do you reckon the most popular wrong answer that students give is? And thirdly, what are the kind of explanations students give for those wrong answers? So pause the video and then just resume whenever you're ready. Okay, so there's the question, what's the area of a triangle? Now, I like this question. I'm biased because I wrote it, but I like it because of that 8 in there. That 8 isn't needed in the calculation for area. And yet, how often are students presented with extra information in questions that isn't needed? And when I wrote this question, I wondered whether students would be desperate to include that 8 in there somewhere. So let's see. So firstly, if I go to advanced, let's get some numbers here. That question's been answered 472 times, and if I go for percentages, we can see that A is by far the most popular answer, and that's the correct one, with 76% of respondents opting for that. Now that's pretty significant, and it's the vast majority of students have got this right, so you may be wondering why on earth I've selected it for question of the week. The reason is, whilst B, C and D don't attract that many student responses, the reasons those students give for the wrong answers reveals so much about the way students think about areas, and they are fundamental misconceptions that we need to identify and resolve. So first things first, how do students explain that the correct answer is 6 times 7 divided by 2? Well, they have some beautiful ways of doing this. I really like this one. This is because the formula for the area of a triangle is base times height divided by 2. 7 is the base, 6 is the height. Very, very simple. I like this because here we get the first mention of the word perpendicular, and perpendicular being very important in the whole of the topic of area. This is maybe my favourite one though. I really like this. The base is 7 and the perpendicular height is 6. You do not need the 8 centimetres as it's the slanted height. I know exactly what they mean there, the slanted height. Love that. So you do base times height and divide your answer by 2. So it's recognising that the 8 isn't needed at all. There's some really interesting ones a bit further down here. A lot of students seem to think 6 times 7 will give the area of a square as opposed to a rectangle. But I know exactly what they mean, and this is a really nice way of explaining it. Then the isosceles triangle is half the square. So to get the area of the triangle, you need to half 6 times 7. That's a nice, really nice visual way of doing it. Some students just prefer the formula, base times height divided by 2. But if I was a student and I wasn't very good at remembering formulas, I'd read that and I'd think, yeah, actually that makes a lot of sense to me there. So absolutely lovely way of explaining things. Now remember, the whole beauty of the website is that if students have got this question wrong, they can benefit from reading as many of these explanations as they like until they find one that makes sense to them. Right, what about B? 6 times 8 times 7. Well, when I wrote that, this was to try and identify students who simply just want to multiply everything together because they're desperate to get that 8 involved somewhere. So let's see if it indeed that has attracted students here. So this is an interesting one. It's the method you use for finding the area of shapes. Only some other shapes you use a different method, but not a triangle. So this student has obviously thought carefully about this one. They've gone to the trouble of writing a pretty detailed explanation, but they're convinced that this particular method where you times all 3 things together is the one you need for a triangle. Maybe because a triangle's got 3 sides, and I don't know. There you go. That's the one that reveals it. I think this is the answer because you times all the numbers together. And the students go a bit further into that. 6 times 8 is 48, and then you do 48 times 7 is 336. So again, these are students who are thinking very, very, very carefully about this one, but are revealing that key misconception that they want to times everything together. I like that as well. On the other answers, where does the 2 come from? So the students ruled out A and C because there's no 2 anywhere on that diagram. And I think the best way to resolve things like this is not often just to kind of hammer the formula down students' throats, because there is a natural inclination for students to include numbers that have been given to them in the question in their answer, because why else would that 8 be there if it wasn't needed? And I think the way to get around that is to keep giving students questions where they don't need all the information that they've been given in there, just to get them into the way of thinking, to just select the information that's needed. What about C, 8 times 7 divided by 2? Now this time students have selected the incorrect height. They've used the slanted height instead of the perpendicular height. Now I think this is an interesting one, is that because students have forgotten that you need perpendicular height? Or more importantly, is that because they know the word perpendicular height but they don't have a clue what it means? And I think that's probably the more likely scenario. Anyway, what are students thinking here? Look at that, 8 times 7 and you divide it by 2. So perfect way of explaining it, but they've selected the wrong height. And again, there you go, I think you times the 8 by 7 because that would make a parallelogram. I think that's a really interesting way of describing it. They can see that if you fit 2 of these together, you're going to get a parallelogram. But then they think to do a parallelogram, you times by the diagonal, not the perpendicular height. And then you just get it all the way down, base times height divided by 2 as it's like a square. So again, these students are selecting the wrong height to times by. And finally, what about D? What about 6 times 7? What's that doing? So let's just have a little flick down to this. 6 times 7. So this is very, very interesting. This one fascinates me. Split the triangles into 2, so the 2 right-angled triangles, and you have 6 times 7 divided by 2. But this then cancels out. So they're realising they've got 2 triangles. They're realising they have to divide it by 2, but the times by 2 for the 2 triangles and the divide by 2 cancels out to make 6 times 7. That would be a fascinating discussion to have with that student. And then maybe the way to resolve that is to get them to physically draw out these 2 triangles and fit them together and just discuss in more detail this concept of doubling and halving. There you go, because you times the base by the height. This is all these students. There's no mention of the dividing by 2 very much, or they're recognising that you have to. More importantly than that, they're recognising that you have to stick 2 shapes together to get this 6 times 7. But then they're forgetting that because you've put 2 shapes together, you have to halve it to get the area of 1 shape. Fascinating stuff. So there you go. There's the kind of insights that we can gain from just looking at a question and students' responses. And I certainly, if I'd never taught area of a triangle before, that would arm me with a load of useful information of the kind of mistakes students make before I went into the classroom to teach it. And more importantly than that, students who may have those misconceptions can really benefit from reading some of the beautiful explanations that students who are getting this question right can have. If you like that question, if you can find a quiz that I've put together on it, so if you just go to the Question Go page, which you can get to just by clicking on the question again, and you scroll down, you get this related quizzes. If you just give that a click, there I've put together areas of simple shapes. That's a selection of 15 questions with a load of different 2D shapes that students have to work out the area of. So you've got your rhombuses, your parallelograms, trapeziums, all the big names in there. And I will be back with a fresh question of the week next week. Take care and bye for now.